Hello everybody, welcome into another lesson. So today we're going to talk about angles of triangles. And I gotta tell you, a good third of this course, actually a little over a third of it, is devoted to triangles. So we definitely got to get used to triangles. But let's talk in general about what triangles are and general stuff about them. Of course, as you know, a triangle is a three-sided polygon, which next lesson we'll talk about angles of polygons. But a triangle is a three-sided polygon. This one is triangle ABC, which you can denote as triangle. Dang it. If I could word it right. A small triangle next to it. This is triangle ABC. You can abbreviate it like that. You have what's called a vertex here, point B, but point A is also a vertex, point C is a vertex. Each of these 3 points, they are singularly a vertex. Plural form of vertex is vertices. So points A, B, and C are the vertices. When you connect the 2 vertices, you get the sides of the triangle. You have side AB, which you can also refer to as side BA. They're the same side. You have side BC, or you can call it side CB. They're the same side. Then you have side AC or side CA. Same side. So a triangle has 3 sides. It also has 3 angles, and tri means 3 angle. So it literally means 3 angles. That's what triangle means. So you have angle A, which can also be referred to as angle BAC or angle CAB. All would refer to this angle right here. Then you have angle B, which you can also refer to as angle ABC or angle CBA. Then you have angle C, which you can also refer to as angle ACB or angle BCA. So that's a little bit of basic information about triangles. Now let's get into some theorems and corollaries about triangles. Well, actually, before that, let's talk about types of triangles. First, we can classify triangles by their sides, by congruent sides, I should say. So, let me draw this bad boy here. If a triangle has no congruent sides, in other words, none of the sides have the same lengths, they're all different lengths, that's called a scalene triangle. This would be considered a scalene triangle. If none of the sides have the same lengths and they're all different. You could think of it as they're all different, so they're scared of each other. Scared, scalene. That's how I remembered it, at least. That's what helped me remember it. Next, we have this one here. If at least 2 of the sides of the triangle are congruent, if at least 2 of them are, you have what's called an isosceles triangle. So if at least 2 of the sides of the triangle are congruent, you have what's called an isosceles triangle. Now, if all 3 of the sides are congruent, so if all 3 are congruent, and these red tick marks, those are congruency markers if you're wondering. If all 3 sides are congruent, you have what is called an equilateral triangle. Equa meaning equal, lateral means side. So if all 3 sides are equal, you therefore have an equilateral triangle. Now, fun fact here. Equilateral triangles are always isosceles triangles because at least 2 of the sides are equal. But an isosceles triangle is not necessarily an equilateral triangle. So that's good to know. So we have classified triangles by their sides or congruent sides. Now let's talk about triangles in terms of angles. We can also classify them by their angles. Let's say we have a triangle and all three angles are acute angles. If all three are acute angles, this is considered an acute triangle. So if we're classifying by angles, all three angles of the triangle are acute, they're acute triangles. I should have kept that triangle because I want to illustrate something here. Let me keep that real quick. So these arc marks I'm making are congruency markers for angles. That means all three angles are congruent to each other. If all three angles of a triangle are congruent, you have what's called an equiangular triangle. That's an equiangular triangle, meaning equal angles. And we'll have a corollary about that in a minute. This will always be an acute triangle. That's the only way an equiangular triangle can occur. Now, another type, if we base it on angles, you have here a triangle with a right angle. If a triangle has a right angle in it, then it's called a right triangle. So this triangle here would be considered a right triangle. And there's a corollary that states a triangle can have at most one right angle or one obtuse angle. It can't have both of them, and it can't have more than one, which we'll cover that in just a minute. Then last but not least, for triangles, if you have a triangle with an obtuse angle, then it's going to be called an obtuse triangle. That's what you would call a triangle with an obtuse angle. It would become an obtuse triangle. So those are the triangles based on angle measurements. Now we need to cover a couple theorems and some corollaries. So let's see here. Let me draw a triangle. Let's see, we'll call this angle 1, this will be angle 2, this will be angle 3. Alright. We have a very important theorem. This one you're actually all probably already familiar with. The sum of the interior angles of a triangle equals 180 degrees. So this theorem states that the sum of the interior angles of a triangle equals 180 degrees. So in other words, if I take the measurement of angle 1 plus the measurement of angle 2 plus the measurement of angle 3, I add all three of those up, I'm going to get 180 degrees for the sum of my interior angles for a triangle. It can't have less than 180, it can't have more than 180. If either of those happen, you don't have a triangle. It's really that simple. It's exactly 180 for the sum of the three angle measurements. Okay. Now we're going to move on to a few corollaries. You're probably wondering, well, what the heck is a corollary? So here's how a corollary is spelled. A corollary is like a sub-theorem of a theorem. They can easily be proven by the same theorem you've already used or by other theorems. So let me draw here a couple of triangles. Let me get my congruency markers ready. All right. So this corollary states that if two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. So this corollary states that if two angles of one triangle are congruent to two angles of another triangle, then the third angles of those triangles are congruent to each other. So in this diagram, I have two triangles. I have triangle ABC and then triangle DEF right next to it. You can see by the congruency markers, angle A is congruent to angle D, and then angle B is congruent to angle E. By that very corollary, then, that would have to mean that angle C is congruent to angle F. The third angles would be congruent then. Angle C would be congruent to angle F. And that makes sense because triangles, again, the sum of the interior angles is 180. The first two angles in both have the exact same measurements, so that could only leave one measurement for the third angles, and they would have to be congruent. So that absolutely makes sense. Now, good news for everybody, we're not doing any proofs today. So we're just going to go through these here, but we are going to put these theorems into practice and corollaries. What's the next corollary? Each angle of an equiangular triangle has a measure of 60 degrees. So each angle of an equiangular triangle has a measure of 60 degrees. Well, that makes sense, right? Equiangular means all three angles are the same. So if you split 180 degrees three ways, you come up with each angle being 60 degrees. That one's pretty self-explanatory. Okay, what's the next one? In a triangle, there can be at most one right angle or one obtuse angle. So in a triangle, there can be at most one right angle or one obtuse angle. Okay. Well, again, the sum of the angle measures of a triangle are 180. Hypothetically, let's entertain this for a second. Let's say I had two right angles in a triangle. Already with two angles, you're at 180, right there. If you any measurement for the third angle will put you over 180. So that doesn't work. It definitely could have at most one right angle. How about an obtuse angle? Well, let's even take the smallest obtuse angle, 91 degrees. Let's say we have two 91 degree angles in the triangle. That's already 182. So with two angles, let alone the third, with two angles you're over 180 already. So that's not going to work. And I promise you, if you try to draw a triangle with more than one right angle or obtuse angle, it's not going to work. You'll end up drawing a quadrilateral unbeknownst to you. So that would explain that one. I have one final corollary, then a theorem. So let's see. We have here the acute angles of a right triangle are complementary. So we have here the acute angles of a right triangle are complementary. So let's illustrate real quick. Alright, I have my right triangle here. I'll have angle 1, I'll have angle 2. Well, this makes sense because you have a right triangle, you already have a 90-degree angle right there. Which means you only have 90 degrees left to work with for the other two angles. So that actually makes sense then. The measure of angle 1 plus the measure of angle 2 would have to equal 90. Alright, so now we have one final theorem to pass on to you today, and then we got some exercises to work out. So let's see here. Let's draw a nice triangle here. Alright, with some lines extended. There's a reason for that. So let's see. I have angle 1, 2, 3. Here's 4. Here's 5. And then here's angle 6. Okay. So I'll explain what's going on here in a second. So this theorem that we're about to learn states that the measure of the not the, because there could be several, I should say an exterior angle of a triangle equals the sum of the two remote interior angles. Okay. So this particular theorem states that the measure of an exterior angle of a triangle equals the sum of the two remote interior angles. So we look at angles 1, 2, and 3. Those are inside the triangle, right? So those are interior angles. Angles 4, 5, and 6 lie outside of the triangle, so therefore they are exterior angles. Well, let's say we wanted to find the measure of angle 4. Let's say we want to find the measure of angle 4. So the measure of angle 4 in this case, which by the way, this is an example of an exterior angle, and that's going to be equal to the sum of the two remote interior angles. Well, remote interior means it can't be touching the angle you're trying to find the sum of. So we can't take angle 2. Granted, it would be supplementary to it, okay? Angle 2 would be supplementary to angle 4, but we can't consider the measurement of angle 2 in this because we need to find the sum of the measures of the two remote interior angles, which are the two angles away from the exterior angle you're trying to find. So angles 1 and 3 would be your two remote interior angles. So in this case, the measure of angle 4 would be equal to the measure of angle 1 plus the measure of angle 3. Or let's say, now I want to find the measure of angle 5. So the measure of angle 5, that's an exterior angle you're trying to find. Well, we can't consider angle 3 because that's touching angle 5. That's adjacent to it. We want the two remote interior ones that are not adjacent to it. So that would be the measurements of angle 1 and 2 would give you the measurement of angle 5. Okay? And then last but not least, let's go for angle 6. So, measure of angle 6, well, that's an exterior angle. Well, we can't consider the measurement of angle 1 because that's an adjacent angle to 6. But 2 and 3 are the two remote interior angles. So the measure of angle 6 would equal the measure of angle 2 plus the measure of angle 3 for this particular problem. So that's what this theorem is saying. Alright. Now, I do have 6 algebra exercises today that's going to incorporate everything. So, no proofs at least, but let's do this. So, alright, so we got those. We can definitely prove that the top, well, not prove, the diagram gives us that the top and bottom lines are parallel to each other. This angle here equals 30 degrees. This angle right here equals 50 degrees. This angle here equals x. This angle here equals y. Okay. So we want to find the values of x and y. So let's go ahead and start. Well, we know the top and bottom lines are parallel, right? And this long line here running this way is a transversal to these two parallel lines, is it not? That would make angle of 30 degrees and x, those would be alternate interior angles. So in other words, x would equal 30 degrees since they're alternate interior angles. So we found x. Easy enough, right? Now what about y? Yes, I suppose you could find this missing angle and then add this to get 180 and then solve for y, but why put yourself through that when we can use the theorem that then an exterior angle measure is equal to the sum of the two interior angle measures. So why put yourself through that? So we know then that x plus 50 degrees would equal y. Well, we know x is 30, so now you have 30 degrees plus 50 degrees equals y, which can only mean that y is equal to 80 degrees. So that means that x equals 30 degrees and y would equal 80 degrees. So those are the solutions for that. Alright, 5 more problems. We'll breeze through this today. What is the next one entail? All right. So there's that hot mess. Now, these two lines here are parallel to each other. This angle is 40 degrees. This is y. This is x. This is 110. Alright, so now we have our angle measurements. We need to go ahead and find x and y. Well, if these two lines are parallel, here's your transversal. x and 110 are corresponding angles, meaning corresponding angles are congruent. So x simply would equal 110 degrees. Well, we just solved for x. That's not so bad. Now there's a quick way to solve for y. Y, remember, the sum of the two remote interior angles equals the measurement of the exterior angle. So in other words, that means y plus 40 degrees equals x. Well, we know x is 110, so y plus 40 degrees equals 110 degrees, which then means that y would simply equal 70 degrees. So x therefore is 110 degrees, y would equal 70 degrees. Alright. So you see where we're starting to put these theorems into practice, where this is all starting to come into play. What's the next one here? Good one. And yes, it has a diagonal right here. Alright, let's set up our markings. This is 50 degrees. Here's x, here's y. Okay. So now we have this quadrilateral split into two right triangles with two right angles, an angle of 50, then we got to figure out x and y. Let's start with x. So in this right triangle here on the right side, we have a 90-degree angle, a 50-degree angle, and x. Remember that corollary that states that the acute angles of a right triangle are complementary. So solving for x will be easy. All we have to do is take x plus 50 degrees, set that equal to 90 degrees, which would then therefore make x equal to 40 degrees. So the measure of angle x equals 40 degrees. Okay. Well, that's great about x. Well, what about y? Because we don't know this angle here, and we certainly don't know that. So what are we going to do? Let's take, whoops, I did forget to mark these lines parallel as the diagram indicated. The diagram shows the left and right side parallel, so that's going to help us significantly. Okay. Notice something. These two lines are parallel. The left line is perpendicular to the bottom base, right? So the left line's perpendicular to the base. Remember that theorem is that if two lines are parallel and a transversal cuts through them and it's perpendicular to one line, it's perpendicular to the other also. So that means the right side is actually perpendicular to the base as well. But the whole perpendicular, the right angle, is the sum of x and y. So to solve for y, you're actually going to have to take x plus y and set that equal to 90. Good news is we know the measurement of angle x, that's 40. So you'll take 40 degrees plus y, set that equal to 90 degrees, which would then make y 50 degrees. So y is 50 and x is 40. That's what you end up getting. So that's why it's so important to know the theorems, so you can find these angle measurements. Alright, what do we got here? No, we actually had 8 problems. I'm sorry. We have 5 more. Draw a nice big triangle for this next one. Alright. This comes down here. And that goes here. All right. That does look like a hot mess, doesn't it? We know for sure that this angle here is a right angle, so that's going to help us. This angle is 65 degrees. That angle is 25 degrees. This angle here is X. This one here is Y up top. Okay then. So here's what we got. We need to solve for X and Y. Well, here's one thing. If we have a right angle here, that means we're gonna have a right angle on the left side. I almost said a left angle. What the heck's a left angle? We'll have a right angle on the left-hand side, okay? So in other words now, this, if you consider both pieces of this as one right triangle, you would solve for Y first, is what you'd actually end up doing, is solve for Y. Let's do that though. Remember, the corollary is that the acute angles of a right triangle are complementary. So that means Y plus 65 degrees would happen to equal 90 degrees, which only means now that Y equals 25 degrees. So we have found the measurement of angle Y. It would be 25 degrees. Okay, we got to get a little creative here to solve for X. They don't tell you that this one here is a right triangle or not. We don't know that. Even this whole piece here, we don't know if it's a right triangle or not. But we're going to have to get a little creative. Do we not have a right triangle here in this small one? Same idea. We have a right angle, so 25 plus the missing angle equals 90. So let's take 90 degrees minus 25 degrees. Well, that would equal 65 degrees. So this angle here would be 65 degrees right here, which means this angle here would also be 65 because vertical angles are congruent, right? So now you have Y and you have 65. We just don't know X. Well, that's okay. All we have to do now is take X plus Y plus 65, set that equal to 180 degrees, because the sum of the three angles even of this triangle will be 180. Well, X we don't know, but Y we know is 25. Then we have plus that 65 degrees equals 180 degrees, which then means X plus 90 degrees equals 180 degrees, which therefore X equals 90 degrees. So in fact this was a right triangle, we just couldn't prove it yet. But the measurements are X would equal 90 degrees and then Y would equal 25 degrees. So yeah, that one is not as bad as it looks. It's just got a lot of parts and pieces, that's all. I have 4 more exercises. Let's see what we're being thrown with next here. Alright. Draw another big triangle. What's next? Right from here to here, okay. And then from down here to down here. Gotcha. Alright. Let's set up our perpendicular markers. Right here and right there. Alright, so this is Y. This here is X. This here is 40 degrees. Okay. Well, where do we begin? what we got to figure out now, we know this whole piece here, this whole lower half, if you merge these two pieces together, this quadrilateral and the smaller triangle, you get one big right triangle, as indicated by that perpendicular marker, right? This suddenly makes it not so bad. This suddenly isn't so bad. Because remember, the acute angles of a right triangle are complementary. So all we have to do now to solve for y is we'll take that y plus 40 degrees, we'll set that equal to 90 degrees, which therefore would render y as 50 degrees. So that's easy enough. Y would equal 50 degrees. Okay, we found y, so what about x? Now consider the whole right half. Merge this quadrilateral with this smaller triangle, you get one big right triangle over here. Now we know y. If we add y and x, they're also complementary. So it's going to work out to be x plus y equals 90 degrees, which means x plus 50 degrees equals 90 degrees, which simply then means that x equals 40 degrees. So you end up getting x having a 40-degree angle, y having a 50-degree angle. So that one actually wasn't all that bad. All right, then I have here 4 more problems. Well, actually, I think 3 more. I'm sorry. I got 3 more. Let me see. Okay, let's set these up here. Interesting shape there, I know. Here's a right angle, and then here's a right angle. So we got 2 right angles there. This is 40 degrees. This is 20 degrees. Here's y. Here's x. All right. So, let's look at this here. I'm going to say, let's go for y first. So, consider the left side. If you merge this smaller triangle with this middle piece, you get one big right triangle, do you not? Well, again, the acute angles of a right triangle are complementary. Now, of course, you're going to have y. You want to solve for y. Plus, you actually have to consider, since we've merged these two into one big right triangle, you're actually going to do 40 plus 20. So you'll have y plus 40 degrees plus 20 degrees equal to 90 degrees, because you've just merged the whole thing. You care about this whole master angle, which means you then get y plus 60 degrees equals 90 degrees, which then simply means that y equals 30 degrees. So we got the measurement for angle y set at 30. Okay, very good. Now, let's focus on the right side here. Merge this middle piece with this smaller triangle here on the right, you get yet another big right triangle. Again, we can apply the same corollary that the acute angles of a right triangle are complementary. So let's do just that. You have the right angle, so really here, that means since we've merged these, you got to consider the sum of x and y as part of being 90. So what it's going to look like is x plus y plus 20 degrees equals 90 degrees, which then means you could do x plus 30 degrees because y was 30 plus 20 degrees equals 90 degrees, which then gives you x plus 50 degrees equals 90 degrees, which then means x is 40 degrees. So what you get in the end is that x equals 40 degrees, y equals 30 degrees. All right, I have two more problems. They're going to be a little bit tougher than what we've done so far today, because one of them even breaks out the system of equations. So, yay, be ready for that. But it's good practice to keep up on our algebra. We definitely need to. All right. So we got that mess there. Here's a right angle, so this is a right triangle. This angle here is x plus 2y. This angle right here is 2x plus y. This angle here is 125 degrees. Okay, so how are we going to go about solving this? Well, we do know 125 degrees. This is 90. Remember that theorem, the measure of the exterior angle of a triangle equals the sum of the two remote interior angles. So what we can do, take our x plus 2y plus our 90, that's going to equal 125. So there's that. And then we can solve for this piece here. We know that 2x plus y plus 125 equals 180, right? So there's our system of equations. Let's simplify this a bit over here. That's going to mean that x plus 2y is equal to 35. And then we'll simply get that 2x plus y is going to equal 55. All right, so now we have a system of equations. The thing I would do, multiply the top equation by 2, you'll get 2x plus 4y equals 70. Then you keep your bottom one, 2x plus y equals 55. So go ahead, subtract your bottom equation. You'll end up getting 3y equals 15, which then means y would equal 5. So now we have identified that y equals 5. So now in order to solve for x, we just put that y value into one of these equations here in the system and we can solve for x. So let's see, 2x plus 5 equals 55, which means that 2x equals 50, which therefore that means x would equal 25. So the values we get for this are that x equals 25 and then y equals 5 by actually doing a system of equations mixed with our geometry theorems. So by now you should begin to see how Algebra 1 and geometry intertwine. They do very much so. And when we get to Algebra 2 trig, you're not going to need as in-depth of geometry as we're doing now, but there are some things you are going to need for it. There will be some things that are going to be helpful. So that is why geometry comes before Algebra 2. Okay, basically I'm drawing a trapezoid here. This is a diagonal. All right. So let's see, the top base is parallel to the bottom base. We do have that going for us. This angle right here is equal to 100 degrees. This angle right here is equal to, I believe that's 5x plus y. Okay. This one's 5x plus y. This one down here is 5x minus y. This one up here is 2x plus y. So yeah, it's going to look like we're going to have a system of equations, but not quite. Not quite. It's actually not as bad as you think. So let's take a look at something here. We notice the top base and bottom base are parallel to each other, correct? Well, this left side serves as a transversal between them. That means that this entire angle here, if you combine the 5x plus y and 5x minus y, merge these two into one, that's the same side interior angle to 100, meaning they're supplementary. So, in other words, if we take 5x plus y plus 5x minus y, we're doing that because the supplementary angle, the same side interior angle, is this whole thing. Because we're not considering the diagonal at the moment. We're only concerned about this transversal here to solve for this master angle. But if we take 5x plus y plus 5x minus y plus 100 degrees, set that equal to 180, since same side interior angles are supplementary, you end up with 10x plus 100 equals 180, which then means 10x would equal 80, which would just give you that x equals 8. So we just found x. X turns out to be 8. Well, great, we got to solve for y. Okay, well, if we look here, again, the top and bottom bases are parallel to each other, right? But this diagonal is a transversal between them. You have 5x minus y, and then you have 2x plus y. Those are alternate interior angles, meaning they're equal to each other, correct? So we will set 5x minus y equal to 2x plus y. Well, we know the value of x is 8, so we're going to take 5 times 8 minus y, set that equal to 2 times 8 plus y, which then means 40 minus y would equal 16 plus y, which then means you get negative 2y is equal to negative 24, which then means that y equals positive 12. So the values of x and y that you're going to get are x equals 8, y equals 12. And you would, alright, here's why. Let me explain something to you. Some people, what they would do is take this x value of 8 and just stick it into any one of these equations. Well, if you do that, let's humor that a second here, alright? Let's just say I put in 5 times 8 minus y, set that equal to 0, as a lot of people would want to. We don't even need to go any further, because that would mean this angle equals 0. You're not going to have a 0 degree angle. That's why that doesn't work so well. So we had to find something else to set that equal to, thus the alternate interior angle. That's why we didn't do it that way. So that's it for this lesson. Next lesson, we are going to talk about angles of polygons. So I hope everybody has a good day. Take care.